If we continue our discussion of esters, the next set of reactions that we're going to talk about are the reactions where we make esters. So the synthesis of esters. And there's three ways that we can make esters. The first way to make an ester is one of the most classic organic chemistry reactions, and that is a Fischer esterification. This is the reaction that you ran in lab when you guys made banana oil. So if we start with a carboxylic acid in the presence of an alcohol, acid, and heat, the product that we get out of this reaction is an ester. And so this is possibly one of my favorite mechanisms, and this was a mechanism that you saw in a previous homework assignment, which was the hydrolysis of the ester to the carboxylic acid. Remember that if we took the ester and treated it with acid and heat, we did a hydrolysis reaction to the carboxylic acid. So this reaction is going in the opposite direction. We have a carboxylic acid as our starting material, which are approximately as reactive as esters. And so both of those types of compounds typically need an acid catalyst in the reaction. And so in this reaction, we have sulfuric acid as our acid. We could have other acids as well. Doesn't have to be sulfuric acid. We could have HCl, we could have various organic acids that are available, but we just need an acid because the role of that acid in this reaction is to activate that carbonyl. And so in this case, we're going to have the oxygen of the carbonyl grab a proton from the sulfuric acid, and that gives us this activated carboxylic acid compound. So this is an activated carboxylic acid. The fact that it's an activated carboxylic acid tells us that it's much more reactive under the conditions of the reaction than this original carboxylic acid. And remember, something that's really been a theme for us over the course of this semester is the fact that oxygens under acidic conditions will protonate just like we see here. So now this structure has resonance stabilization, where we can pull those electrons up to the oxygen and reveal that carbocation. That shows us that the carbon is electrophilic, it has a fair amount of positive charge, and that our nucleophile of the alcohol can attack at either this carbocation or its resonance structure where the carbonyl was intact. So if we have the alcohol attack right there, that's going to give us a tetrahedral intermediate that looks like this. Whenever we have the tetrahedral intermediates, it's always about who the best leaving group is going to be. If this tetrahedral intermediate collapses, my best leaving group is going to be this molecule of ethanol that just attacked. So once again, all the steps in this mechanism are reversible. But what we need in order to form our product is we need this molecule of ethanol to remain intact. So we're going to have a base in our reaction, which will be the conjugate base of sulfuric acid. Remove that proton, give the electrons to the oxygen, and what that does for us is that makes it such that this molecule of ethanol is no longer our best leaving group. So my new tetrahedral intermediate looks like this. This molecule is under acidic conditions. We know that oxygens under acidic conditions will protonate. Any one of these oxygens can pick up a proton under the conditions of the reaction. And because this is a reversible process, they all can, they all will, and they all lead us to various points in the reaction. But the productive part of the reaction that leads us to that ester product is going to be where one of these OHs pick up a proton from our molecule of acid. So in this case, we could have this oxygen pick up that proton, and that's going to give us this tetrahedral intermediate. where from this tetrahedral intermediate, the possible leaving groups that we have are a hydroxide ion, an ethoxide ion, and a molecule of water. So that molecule of water is my best leaving group under the conditions of this reaction. So that oxygen can either take its electrons and leave, or that oxygen can take its electrons and be pushed out with the assistance from one of the lone pairs on my adjacent oxygens. So I can take that lone pair and push it towards the carbon. I can kick out that molecule of water, and that leads me to this structure. Okay, this structure is really the activated ester that we saw in our ester hydrolysis mechanism. So the only thing left to happen in order to get to our final product is for a base in our reaction, which in this case is the conjugate base of sulfuric acid, to remove that proton and give me my final product, which is that one there. So that overall in this reaction, the products that I made are this ester, and I also made a molecule of water when my tetrahedral intermediate collapsed. So in the lab, you made banana oil. You took acetic acid in the presence of isoamyl alcohol, sulfuric acid, and heat, and you made banana oil. We could take butanoic acid here, which is a carboxylic acid that smells like vomit, in the presence of ethanol, sulfuric acid, and heat, and make this compound right here, which is ethyl butanoate, which smells like pineapple. This is the fragrant compound that smells like rum. Here we have peach, wintergreen, and strawberry. The second way to synthesize an ester is through the use of diazomethane as our reagent. So it has a formula of CH2N2. The limitation on this reaction is that it makes methyl esters only. There's no such thing as diazoethane or diazopropane. This reaction is specific to making methyl esters. So in the mechanism for this reaction, we have our carboxylic acid in a reaction with diazomethane. Remember that diazomethane is very unstable. We have to use specialized glassware, very specialized conditions in order to use that reagent. We use it at very dilute concentrations with a lot of safety precautions to prevent any sort of explosion. And so in this reaction, your diazomethane is going to pick up a proton from your carboxylic acid, and that's going to give us a carboxylate ion and this species here. Now, this particular structure has N2 as its leaving group, and N2 is one of nature's best leaving groups. As this oxygen attacks that carbon, kicks out our molecule of N2, that N2 is going to bubble right out of our solution, and that's going to give us a very clean reaction where we make our methyl ester plus that molecule of nitrogen gas. The third way that we can make an ester is with an SN2 reaction between a carboxylic acid and a primary or secondary alkyl halide. So in this reaction, we require a primary or secondary alkyl halide along with a base like potassium carbonate. So under the conditions of the mechanism, my carboxylic acid will first react with my base. So if I have carbonate as my anion, that can remove a proton from my carboxylic acid, and that's going to give me the carboxylate ion plus a molecule of bicarbonate in this case. Now that I have this carboxylate ion, this can act as a nucleophile in an SN2 reaction with a methyl primary or secondary alkyl halide. So that can attack at that carbon, kick out my iodide, and that's going to give me my final ester product in this reaction. So think about this question. If banana oil were your synthetic target, come up with a few ways that you could make banana oil. You could have a carboxylic acid as your starting material. You might have an anhydride as your starting material. You might have an acid chloride as your starting material. Think about how you might accomplish that synthesis. So here's 4 ways that I came up with. In this way, we could do what you did in lab. We could take ethanoic acid or acetic acid in the presence of an alcohol, sulfuric acid, and heat, and through a Fischer esterification, make banana oil. We could also use acetic acid or ethanoic acid in the presence of a base like potassium carbonate and our primary alkyl halide that we have here in order to make banana oil. We could react an acid chloride with an alcohol to make banana oil. We could react an anhydride with the alcohol to make banana oil.